everyone. We are going to be working today on some more double integrals. I've made another feeble attempt to draw one, but can you imagine that we have a rectangular region on the XY plane, and that region meets a surface at the top called Z equals XY, which would be this guy here. And so when you find the double integral of this rectangular region of that function, what you're finding is the volume of this solid. And some of the questions in the homework ask you to find the volume of something, and this is essentially just a way of telling you that what you're being asked really to find is a double integral. Now, you're going to see some notation where the rectangular region is described using this notation. These two letters are the x values. So I want you to think x is a to x equals b, and these are the y values. So the convention is x comes first, right? So if they went and said to you the interval was 2, 3 cross 4, 5, you would know that that just meant that the x's were from 2 to 3 and the y's were from 4 to 5, okay? It's just a notation thing in case you haven't seen it before. It's still a double integral, right? And you're still doing all the things that we were doing before. Also, before we start looking at some questions, sometimes you can have your function separated out. In other words, the function z can be written as two distinct functions multiplied together. And so an example of that might be that question, that function there. That can be written like that. So if you have your function, right, your f of xy guy, if you can separate it, that's what I call separating, into all x's times all y's, then when you're doing the double integral, that guy, you are allowed to split it into that fella and that fella, which tends to make the calculations a lot easier, right? And we did mention that yesterday. You are also, because it's rectangular, in other words, the limits on the x's and the limits on the y's are both numbers, you are allowed to take a double integral where you do the x first and the y second, and you can switch places and do the y first and the x second. The only thing you have to make sure that if x is first, then the limits of x's get done, and then the limits with y get done after that. And if you switch places, then the limits on the y's get done first, and then you do the limits on the x's second. Sometimes that can help. Can you imagine there might be a situation where it's easier to integrate with respect to x first, and then plug in numbers and then do the y second, right? I can imagine a situation where that might well work well. So sometimes you separate them because the working is easier. Sometimes you change the order. If you decide not to separate them or not to change the order, you'll still get the right answer, right? But it might take you a bit longer. Any questions about that? Are we quite comfortable about some of the things I've mentioned? Right. So let's jump right into a version. No particular reason, I just happen to have it open at 12. We're finding a double integral over a region R. It's x secant squared y dA. dA is just a short way of saying that. Basically, you're integrating over an area, you're integrating over x and y. The region R in this question is described using this notation. So this is going to be from y equals 0 to y equals pi upon 4. It's going to be x equals 0 to x equals 2. There's going to be an x, there's going to be a secant squared y. Since I'm doing x's first and then y second, I'll write it that way. Would you agree that this one is separable? So what I'm going to do is I'm going to do the integral from 0 to pi upon 4 and do secant squared y dy and multiply it by the integral from x equals 0 to 2 of x. Right. This one first, it's 1/2 x squared, evaluated at x equals 0 and x equals 2. And what does that get me? 1/2 times 4, which is 4, take away nothing. That guy gets me 4. Okay. I know it's Calc 2 and it could have been 6 months ago, but you should still be able to remember.
So the 1/2, wouldn't it be 2?
Did you all catch that? Did I make a mistake? Yes. What's secant squared?
Tangent y.
Great. So the integral of secant squared is tangent y from 0 to pi upon 4. That's the tan of pi upon 4. Subtract the tan of 0. The tan of pi upon 4 is 1. 1 take away 0 times 2. And the final answer is a very nice answer. It's just 2. Pretty straightforward, no real frills as long as you do it. Now, could I have left them together? Of course I could. Would I have got 2? Yeah. But I think separating did make things a little bit quicker. Let's have a look at that one. Where am I off to? I'm just scrolling up and down, see what I can see. Okay, this one is phrased in terms of finding a volume. So it says, find the volume. So that's the key, it's going to be a double integral of the solid. Of course, they're all solids. Of a function that's a hyperbolic. I don't need to know that that's what it's called, but this is what the surface looks like. Right, that's essentially the f of xy. It's this guy. And it's above the rectangle R, and it's described using that notation. So the key here is volume. So I'm going to look at finding the double integral. And the x's go from -1 to 1, and the y's go from 1 to 2. Are you comfortable about that notation generates the limits of integration? The function that we're going to be integrating is 3y squared take away x squared plus 2. In the order I've written it, I'm going to do the x's first and the y second. In this question, couldn't I switch places if I felt like it? Couldn't I do the y's first and the x's second? And it would have been the same result. So it's going to be the integral from y equals 1 to y equals 2. But before that, we're going to do this guy. With respect to x, the integral of 3y squared is 3y squared x, because we consider y a constant. The integral of this x squared by the power rule, and the integral of 2 gets me that. And we're going to do from x equals -1 to x equals 1. So it's going to go like this. If you plug in 1, you're going to get 3y squared. Take away a third, add 2. Subtract. If you plug in -1, you're going to get -3y squared. Negative times another negative, so you're going to get plus a third. And you're going to get -2. Let's see what that becomes. 3y squared, take away negative is adding 3, so you get 6y squared. Negative a third, add 2, take away, what if I put that there? That's a negative, I don't know what's going on here. So that guy, take away that way is -2/3, add 4. 4 take away 2/3 is 10/3. And then you can add 1 to the power. And divide by the new power. And then evaluate that from -1 to 2 and then dot, 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 if you go and finish. Yes.
Let's see. So I think you dropped the negative in the last one because the 2 is positive. Because it's the equation is +2.
Oh, that's a +2. Okay. Did I count that? Let's see. That's 2 and that's +2, so that gets me 4. And I've got negative.
No, that. Here, I'll just circle it with the annotation.
Okay. I'm trying to find out what I've done wrong. Right. This
I've been working on this independently, and I'm still getting the same as you, Professor.
Okay. Well, sometimes I get things right, but I'd rather you tell me about it. So if we're doing that, I'm cool.
So it'd be minus -3y squared minus 1/3 plus 2.
Okay. 2 lots of -1 get you -2. So not +2.
Right.
And then
But
later
saw
on you
that negative,
subtract
so
it.
I distributed the negative, and I don't
Okay.
know if I managed to get
Well,
that.
no, what you would have had is -3, add a 2, take away a third, add another 2. And all of that.
If you look at
becomes
the
a
original
10x.
equation, the 2 is positive to begin with. Oh, they're because of the negative.
We good?
Yeah, we're good.
Right, not a problem. I'd rather check it and I was right than let something wrong go by. Okay, we've kind of finished with that one, right? Can you imagine you plugged in some numbers and just be careful, you should be good. Oh yeah, okay. Not going to do all of this question, just going to set it up. There's a double integral happening. This one, the x's go from 0 to 2. And the y's go from 0 to 1. And the function looks like this guy. And they have one of those DAs, but I'm replacing the DA with that, right? So after a couple of lines, this is what you've got. How do you think we should tackle this one? Is there anything that might make your life a little bit easier?
Separable.
It's separable.
Agreed. So can you imagine doing that guy totally separate from it? Doing that guy. By the way, I'd probably call that 3 plus 3x squared. But if you do that, can you imagine that those are just two relatively straightforward integrals? Just for curiosity, does anyone remember what the integral of 1 over 1 plus y squared is? You know, just get some of the cobwebs out.
Arctangent.
Trigonometric, isn't it?
It is, but what is the answer? I think you might have said it well, but I didn't catch it.
The arctangent.
Yeah, you just said that in bad word, didn't you? Inverse tangent.
Is this another one of those Scottish things, or is this just mathematical opinion?
It's one of the, he's just been nitpicky, but I hate in arctans and arc anythings. It's such an archaic term, we shouldn't use it.
You should have seen my high school calculus teacher. He was the exact opposite. He despised the -1 notation.
You just can't win for losing. Is that guy 80 or just a weird American?
He is a very strange character.
Okay, weird
What if
American.
we just compromised on calling it inverse tangent?
Well, that's what I call. I'm not compromising. I'm right. In one particular school of thought, I'm not. An absolute right. Ask my wife; she'll tell you I'm not absolutely right. And this one I'm putting in because I just noticed how ugly it is. And it wasn't, it didn't look ugly until I scanned it for a second time and thought, oh, that is ugly.
Hey, Professor.
Yes, Joel.
I noticed that there's some people missing.
Do you think there's something wrong?
There
they-
is something. I was waiting about 15 minutes and Zoom kept indicating that the meeting had not started yet.
I've been here and we've been here, so Zoom's being weird.
Yeah, so I emailed Tim and he didn't respond and he's not on the meeting either. I emailed him and said, hey, are you waiting like me? I'm just letting you know. I don't know.
Tim,
He was here.
well, Tim is here. Well, he's here.
I'm here.
Tim,
I'm
how's it
good.
going? Tim's good now.
Oh, okay.
I've been here the whole time. I just had my when he writes, it gets all buggy, and so I turn my camera off because it makes his writing go faster.
Okay, roger that. So some people are getting the indication that you haven't started the meeting for whatever it's worth. Just thought
Well,
I'd let you.
thanks. Yeah. There should be 2 more people in this class, so there are 2 missing. Okay, let's have a look at this guy. Now, when I looked at it, I thought, well, I mean, I know how I could do it, but I'm not wanting to do it this way. Couldn't I foil that horrible thing out and have a polynomial about this big? Right? And I don't want to do that. In fact, if you put the power of 40 here, which you could have done in this question, that would have been just totally impractical. So we've got to figure out how to do this. And the answer is a U sub. But this is going to be the first time you've ever seen a U sub that looks like this. And I'm going to do my U sub over here. What do you think it would be? I want you to think of that as 2x plus 1 to the power of 4. Imagine what you would have done there, right? If
It
that had
would
been
be
2.
the du would be the partial derivative with respect to x, which would just be 2.
Okay, so in the way I do
I
it,
mean, yeah, 2.
so yeah, I agree with you. It's going to be 2. So I do a U sub, and the U sub is still that guy in the brackets. So can you imagine that's 2x squared plus y cubed, right? Something weird like that, right? Y is considered a constant. So that is a valid U sub. Now, normally when you do U subs, you differentiate with, in this case, with respect to x. There's the 2 that you're talking about, Sally, I agree? Right. What I would do next is do a crossover and then isolate the dx. So far, so good. Agreed? Right. Now, going to switch places because I like to write on my right-hand side. This is going to be the integral from y equals 0 to y equals 1. This fella I'm going to write down as u to the power of 4 times 1/2 du dy. So this piece here has now become that guy. And that's going to turn into the integral of 1/2 u to the 4 du. That's going to become power rule. Add 1 to the power, divide by the new power. And I'm going to return back to the original. And the original was 2x plus y. So it's 2x plus y to the power of 1. And at this point, I'll now put the limits of integration back in. Are you comfortable about how we did the beginning part of that process? Right. Now, what's going to happen now is simply just plug in x equals 1 and then x equals 0 in, and we'll see what we get. So it's going to be 1/10, 2 plus y to the power of 5, take away 1/10, well, 0 plus y is just y, times y to the 5, dy. You comfortable with that line? Replace the x with 1, take away, replace the x with 0. Now, that guy is doable now. Would you agree this piece is easy? Isn't this piece just going to be a power rule? How might you tackle 2 plus y to the power of 5? How would
You could do another U sub, and that would just be 1.
Yeah, and off you go and do your thing. So at that point, I'm just going to stop. Do you see that there are a little idiosyncrasies now when you're dealing with two variables? It's still a U sub, even although the U sub itself looked a bit weird, right? It had X's and Y's in it. So helpful technique, much better than the alternate, which would simply have been to FOIL the whole thing out. And I don't really feel I would want to do that. Now, question 17 is a plane 3x plus 2y plus z equals 12. So that's a three-dimensional plane. And we are being asked to find out what the volume would be above this rectangular region. And again, I'm only going to do part of this question. Well, I know that the volume is going to be the integral from y equals -4 first to 1, and then integral from x equals 0 to 1. And here I should be doing my function in terms of x and y. Yet this doesn't look quite the way it needs to be written. Is there a way of rearranging this so I can have x's and y's here?
I mean, I suppose we could figure out the relationship of z to x or y.
How about this one then? Would that work? Great. Z, right? So you put in 12, take away 3x minus 2y. And off you go and do the usual and you're finished.
Why wouldn't we have the 3x plus 2y?
Why wouldn't we have 3x plus 2y? Is that your question?
Yeah,
Why
from the original equation, because the
Well,
12
well,
minus
if you
3x minus 2y is just the z part of that formula.
right, z is our function of x and y. So we're basically making this piece the z. Now, if you tell me this is equal to 12, if I subtract 3x from both sides and I subtract 2y's, isn't that what z is equal to in terms of x and y? And the z is the guy that goes here. Does that make sense?
Kinda, yeah.
Right, let's do another one. Suppose you were looking at this surface. And you recognize that as a sphere, radius 1, center of the origin. But if I wanted to find the volume above a rectangle going up to the top of a sphere, can you imagine the rectangle and you went up so you'd have a funny little guy? If I wanted to find that volume, I would have to find what the surface is in terms of z, the vertical distance. So that would be the guy that would go here.
Okay, so then that would just give us our volume. We wouldn't need to like plug it into our initial equation.
Yeah, you rearrange your initial surface equation in terms of z, and whatever that new version in terms of z is what goes here.
Oh, okay, that makes sense.
Right, so that's kind of what's happening here. Well, once you've set this up, I'm stopping there. Would you agree the question's pretty much what you see is what you get? Let's show you an extra little kick in the tail. I know it's around, so I'll pick my point.
Okay, I got a question about that. The
Okay.
compliment. So, yeah. So you're saying that we're measuring the volume.
Right, so the volume is on the floor, right? So the rectangular region is x going from 0 to 1.
Yes,
and the
but
y
it's-
is going, well, it's over here. So the y is going from -4 to +1. So the region on the floor would look something like that.
But when you gave the x plus y plus z squared equals 1.
Oh,
That's
that's a different question. I just did that as a separate example.
Okay.
Right.
You're not really measuring the volume of a sphere.
No. What if you were doing this question, right? what you would have is half a sphere inside the XYZ plane, right?
Half a, okay, got it.
And
half a
then you'd
sphere.
have a rectangular region,
I got
and
you.
you're going to be doing this weird volume. God, it's not even possible to draw. But you can run something inside a sphere that you went up,
I got
and
it.
you'd have a funny little curved dome to it.
Yeah, column.
You're finding that, yeah, a column with a curved surface on the top. That would be the
Gotcha.
volume that you would be finding in this second situation. Here, that's a flat plane. So what you've got is some kind of plane, an angled plane like this, and then this fella's coming up and this is going up. So the volume that you're looking at would look,
Yep.
It looked like a rectangle that had a diagonal cut through it. I guess that's what
Cool.
the solid would look like. And
It-
again, what you're finding is the volume.
Everything that we're doing involves one end of the space having a flat surface, which is planar with XY, correct?
Correct. So we're talking about even more specific than that. You're correct. Rectangular regions on the XY plane, right?
With a contour on one end.
With the vertical distance generating a surface contour.
Yep.
Yeah, that's what we're doing. So let's add to that as our one last kind of question. Suppose I had a surface and Z is equal to, so we'll make it nice and easy again. And the surface is Z equals 2x squared plus y. No idea what that looks like, but it's fine. And we're going to do x from, oh, let's not do it. Yeah, why not? X is from 0 to 1 because I have no imagination. And y equals -1 to 2, right? Now, a normal volume would be y equals -1 to y equals 2, x equals 0 to x equals 1, and the function would look very boring, right? Nothing special. So now I'm going to add something. I don't want to know the volume of this shape. By that I mean I don't want to know the volume on the plane, on the floor. So x goes from 0 to 1, and y goes from -1 to 2. So this rectangular region meets with this surface Z, right? It's up here somewhere, right? I don't want to know this volume, right? That shape. I want to know the volume if you started not on the XY plane, but you started at Z equals 1. So the same rectangle, but a little bit higher. Okay, so that's the alteration to the standard question. So the first part I'm going to do is calculate that the way I always would. So we'll need to go through that first. So I don't know if I should call it V, but I'll call it V now. So it's going to be from -1 to 2. And that guy's going to get me 2/3 x cubed. And that guy's going to get me xy. And I'm going to do it from x equals 0 to x equals 1. And then we'll integrate with y after that. Right, you plug in 1, you get 2/3. You plug in 1, you get y. Take away, you plug in 0, plug in 0. That's how you get that, right? Because these essentially annihilate each other. So what you've now got is this fella. So it's 2/3 y plus 1/2 y squared, evaluated there. So it's going to be 2/3 times 2 plus 1/2 times 2 squared. Take away 2/3 times -1 plus 1/2 times -1 squared. So that's 4/3 add 2, take away a -2/3, so let's add 2/3, and that's what, 1/2, take away 1/2. That's 4 take away 1/2, so I hope I got this correct. Right now, it would be 7/2. So if I wanted, starting on the XY plane, going up and meeting this surface, the volume of this solid would be 7/2, right? That's what we've actually calculated right now. So how do you cope with the fact that we're not using the floor, the XY plane? We're actually using Z equals 1. How will we find this new volume? It's not as difficult as it sounds, actually.
So I could see, it occurs to me that you could have intervened between the integral of X and the integral of Y and taken an infinitely small slice and up the bias. In other words, scale the base, the 0 base up to 1,
Uh-huh.
calculated the slice, and then integrated the Y side.
Oh, and all of that would have worked, but there's a slightly easier way to realize. Isn't the shape we want the whole volume? Take away the bit in the bottom. Does that make sense? Taking the whole volume and then just cutting off the bottom. And what you said would have worked, but isn't that bottom just a cuboid? And so, technically speaking, I've probably chosen a bad function here. So I'm not going to make that Z equals 1. I'm going to make that Z equals 100. That'll make it so it's below the shape, but it's still going to be the same thing. So you're going to take away the volume of the bottom. And so it's going to be 7/2, take away, well, in this direction, it's 3, and in this direction, it's 2. So it's 3 times 2 times, that's why I had to change that to a very small number. So I didn't, destroy too much of the shape. So we have 7/2, take away basically 6/100. And so it would be 3.5, take away that guy, and you'd get 3.4. So if you wanted to slice something at Z equals 1, provided the surface is up there, right? Couldn't you do it? Could probably do a Z equals 2 and a Z equals 3 if the Z was high enough. The Z I've got is really very low. So taking 1 off is too much. If you do a double integral and the answer is 0 and you haven't made a mistake, what's that telling you about the interaction of the surface and the XY plane?
They're coplanar.
What do you mean by the coplanar? They're parallel to each other?
They would have to be sitting, they're both flat and they both have to be on the same plane, right?
Well, that would be one way of it happening. Yes, but that would just be a rectangle on the floor, and that would generate exactly that. But in general, you can actually do better than that. Or different from that, maybe not better. Do you remember doing in Calc 2 the area under a curve that looked like that? You remember? And couldn't the area, in fact, be 0? So we're not physically talking about the area, but we're talking about the area under the curve. Remember, net area, I think, was the phrase that would be used here. If you do a double integral, right, or some function, and the answer happens to be 0, what you could be looking at, can you imagine a surface that was, and this was the XY plane, where the bit above was the exact same volume as the piece below? Couldn't that generate a 0 double integral? That makes sense. In fact, now that I think about it, if you have a sphere centered at the origin, won't the double integral of that sphere be 0? Because won't the top half be exactly the same as the underneath the XY axis half?
So basically, if it's symmetrical in the positive or negative direction.
Yes. So Z is plus generates positive volumes when the Z is below the x-axis. So it is possible, isn't it, for you to do a double integral of a function? Now let's do dA for quickness. And couldn't you get -10 as an answer? Couldn't that happen if all the surface was below the XY plane? So we talk about double integrals finding volumes, but that's just one particular application. Can't we sometimes just think of double integrals as representing the net volume, right? How much is more above or below than the rest of the shape? Okay. Any other questions about that? Because that was a little bit
Professor,
off the side. Yes.
where did you get the two?
Could you be I'm not hearing you very clearly. Could you be a bit louder, please?
Do you know, like, where did you get the 3 times 2? I see where you got the 3, but I don't know where you got the 2.
Oh, I hope I got it from the rectangle dimensions. So if my integral, well, now I have, my integral was 2 going that way and 3 going that way. So I made this, I assumed that my rectangle was 6 and that my height was whatever we decided to cut it off.
Awesome, thank you.
Rose, you had your hand up. What's the question?
Are we at a point in the lecture where we can go over a homework from yesterday?
We can do that at the end if you want
Okay.
to wait. Okay. Hopefully you don't have a class to go to. Are there any other questions about these double integrals that we have done? So sometimes they talk about them being volumes, and other times they just talk about them being a double integral. And so especially when it's a double integral, zeros and negatives can and probably will happen. I'm doing a quick scan through it to see if there's any situation I've missed.
So you
Here's one.
you showed that problem with the X, Y, and the Z in the equation.
Yeah.
And the implication is that we're calculating the Z because they're asking for the XY volume.
Yes, we're doing the volume from a rectangle going upwards in the Z direction.
How would you indicate in that equation that there's an offset on the Z?
Oh, the question was phrased. I'll try and find the one that does that. It says find the volume of a solid above. Yeah, right, here we go. Question 9 was an example of this. And it says find the volume of a solid enclosed by a parabola Z equals and the plane Z equals 1. And then they tell you the X and Y variables. So it's and the plane Z equals 1 was the clue there, that there's going to be a flat plane. If I said to you Z equals 1, isn't that a plane parallel to the XY, 1 above the floor?
Sure, but is there any way of indicating that in the equation itself? The Z equals 12
No,
minus.
not in any meaningful way.
Okay,
So the Z is fixed. That is the relationship of the surface. And the surface doesn't care where you start the base from. The surface is still going to be 12 minus 3x minus 2y. Okay, if that is the case, and by that I mean, are we good with our questions? Right. Then let's move on to the next section where we are going to do double integrals. As soon as I find the damn thing, over non-rectangular general regions. Okay, so this is going to be section 15.2. Trying to find what section is called. It's integration, actually double integrals. Integration over general regions. So general region is if you ain't a rectangle, right? So anything on the floor, so we're still doing an XY region on the floor, and we're going to project it vertically upwards and it's going to meet the surface, but the guy in the bottom isn't a rectangle anymore, right? It will be things like triangles and halves of circles and all sorts of cool stuff, right? So far, so good. Now, let's show you an example of a double integral that looks like that. Suppose y equals x to y equals 2x plus 1. And x equals 1 to x equals 2. And the function was x squared plus y. And I'm doing a dy dx just to be different. And I don't think you can see that, can you? Not sure. This is an example. Right, here we go. This is an example of an integral over a general region. So x is going from 1 to 2, y is going from 2x plus 1 to 2x. This is the function. This is basically z equals f of xy. We're doing y first, you can tell because of that, and then we're doing x next. A little bracket around that to emphasize things. So x is going to go from 1 to 2. Now, if you integrate this expression with respect to y, you will get x squared y plus 1/2 y squared. Are you happy about that? The integral of x squared plus y with respect to y generates these. You will then evaluate it, not at your usual numbers, because now the x and the y are functions of x. And so x equals 1 to x equals 2. If you plug in y is 2x plus 1, you get x squared times 2x plus 1 plus 1/2 of 2x plus 1 squared. Take away, if you plug in x here, you get x cubed plus 1/2 x squared. Are you okay with those substitutions? Instead of substituting in numbers, we're now substituting in expressions involving x. Now, typically what happens in the next line or so is I'm going to take all of this and just tidy it up. So if you distribute, you get 2x cubed plus x squared. If you square that guy, you get 4x squared, but half of 4x squared gets you 2x squared. You get a 4x, but half of 4x is 2x, and you get a 1 and 1/2 of 1, you get a half. So that's that guy. Take away this guy. And then if I collect like terms, what do you get? 2x cubed, take away that guy, leaves me with 1x cubed. And I take that x squared, add 2 of them, then take that away. And so I get 3 take away 1/2 is 2.5, 2.5 is 5/2. And then I get 2x on its own, and then I get 1/2. Are you comfortable about that? Anything that doesn't make sense? Apart from the fact maybe I can't count. Right, at this point here, it's really just good old fashioned Calc 2, power rule. 3, so power rule, evaluated at 1 and at 2. If you plug in 2, you get 4. If you plug in 2, you get 8, so that's 46. Plug in 2, you get 4. Plug in 2, you get 1. Then you get that guy, that guy, that guy, and that guy. And then you get some ugly fraction that you would get, and you'd be finished. So what we're looking at here is a double integral where one of the limits of integration is not a sequence of numbers, but contains a variable. Are we okay with that process? It's really just an adaptation of something that we would have done if everything had been numbers. Are we good? Can't see any nods or crosses, so I'm going to assume that we're good. Well, let's see if we can give you a double integral over a region R of some function. dA, so that's the general way to write it down. And we are going to be told that R is this fella. And it's made up of a straight line and a straight line and a straight line. It's made up of that triangle. And this guy, the straight line, is y equals 3 take away x. And this guy is 0. And this guy is 3. And this guy also happens to be 3. So we are being asked, oh, and I'll have to tell you f of xy is. Let's suppose f of xy is just x squared plus y squared, right? Nice simple function. So we're being asked to find the double integral of this function over this triangular region. You see it's a triangle, not a rectangle. So can you imagine above this, there's a curve. And we're trying to find what that volume looks like. Now, if the curve was up here, like something like that, you'd go this guy, this guy, and this guy. Can you imagine it would look like some kind of weird triangular region with a curved surface at the top? I should give up trying to draw these things. They don't help. Right, now we need to set up what the integrals look like. Now I know who f of xy is, so that's easy. dA has two possible choices. Right. Now, if I want to describe this region, I could tell you that x goes from 0 to 3. And what does the y values go? Right. If you take a typical little rectangular guy, can you see that the y goes from 0 to the point on the line? That is how you describe this region. Are you comfortable how I describe that triangle as x goes from 0 to 3 and the y goes from 0 to 3 minus x? Okay, now this information is going to be transferred onto these limits of integration. So which one do we do first? A dy or a dx? Because that is important.
Should I start with the dy?
Agreed. And if you're going to do the dy, then shouldn't the y go from 0 to 3 minus x? Do you see how my little putting y equals kind of helps these stories a little bit more? Because now it's clear that y is 0 and y is 3x. Now, what will the second variables be? What will the x's be? Well, 0 to 3. Are you comfortable with what I just did there? How to set up this thing? And then, yeah, and then you just go and do the usual way. And we're going to do plenty of these tomorrow. I just wanted to give you a kind of setup. I would like to, no, I won't, because I've got something else I need to do. Okay, last name, bye-bye. And if you have a question, hang about it then, and I'll try and answer it. And Rosie, I will look forward to your question, if that's what you're asking.
Yeah, so
Thank you.
Bye-bye.
I did the homework up to problem 11. What
Uh-huh.
homework or what question should we finish up to on 15.2?
Well, we still have a few days, so we'll get all of it done. Oh, what can you do right now?
Yeah,
Probably only a couple of questions. We've only really touched on this. We haven't really done any, you finished 15.1, right? We've done everything that you need to know to finish 15.1. In 15.2, we've really just done the intro. I guess I could have a quick look and see what that looks like. You'll be able to do question 1, questions 2, 3. Oh, more than I thought. You should be able to do the first 5, I would predict.
okay. Can we go over question 5 from 5.1?
Sure. What does it look like?
Double integral. First one is from 0 to 1. Second one is from 0 to 1. 4xy square root of x squared plus y squared dy dx.
Since they're doing it that way, y is 0, y is 1, then the x equals 0, right? And the x equals 1, right? We got that. I need to integrate this guy with respect to y. And what I'm looking at here is a u sub. And the u sub I'm going to choose is that one. Now, if you differentiate this with respect to x, you get 2x because y squared is considered a constant. You then do your crossover. And then you divide by 2. Oops, let's get this right. There. You isolate the dx by dividing by 2x. So this integral becomes and stays 0 to 1. This one, I'm not going to write the limit integration because I'm doing a u sub, but it's going to be right now 4xy square root of u. Okay. And instead of since I'm doing y as a variable, that's a y, that's a y, that's a y, that's a y, and that's y, right? I'm fixed. So we get 1 over 2y du. Okay, apart from the fact I forgot which one was a variable, I know it's y that's a variable because here, right, I'm differentiating with respect to y, or I'm integrating. So I know it was y. So the math is the same, the variable switch. So we're now going to have x equals 0 to x equals 1. 2 and 2 is going to cancel, y and y is going to cancel. Looks like I've got an x left over, but I don't care about x's. They're just constants. And I have a 2 left over, and I have a square root of u du. Are you comfortable with that?
Yes.
Right. What I'm now going to do is call that guy u to the half. And now I'll use the power rule. Add 1 to the power. Divide by the new power is why I get that. Return it back to the original variables. This guy is basically the square root of somebody cubed. So it's the square root of somebody cubed. Evaluated at y equals 0 to y equals 1. So the 4/3 x u to 3/2 becomes 4/3 x, this guy. Now, continue with that. We got a 0 to 1 going on. It's going to be 4/3 x. If you plug in 1 here, you get the square root of x squared plus 1 cubed. Take away, when you plug in y equals 0, you get 4/3 x, and you plug y equals 0, you get the square root of x squared cubed dx. And it's a bit ugly, but it will be doable. I've got this guy, and we're just going to call it x squared plus 1 to the 3/2. That guy's actually just x cubed, so you get 4/3 x cubed times x to the 4. And so that's what our integral looks like. Now that guy is a Calc 2 integral. I can do this one by just the power rule. And how am I going to integrate this? Four-thirds x squared plus 1 to the power of 3/2. How am I going to integrate that guy?
Multiply by 2/5 and then change the exponent.
Oh, no, not allowed to. If it was 2x plus 1, that would be a a good way of tackling it. But since it's an x squared plus 1 in the brackets, we can't do that version of the power rule.
Is this
So-
a U sub?
It is a U sub, right? And the U sub that you're going to have to use is x squared plus 1, right? And after another 10 minutes, you will eventually get it to work out. And I'm hoping that x equals 0 and x equals 1 makes the numbers, you know, nice when you're finished.
Okay. Thanks for your help.